University for geodynamics. So he happened to work with this geochemist, Graham Pearson, for this work. So this work basically is a combination of geochemistry and with a little bit of geodynamic modeling to reveal the process of the fate of the continental lithospheric mantle. And in addition, Graham Pearson says he moved to University of Alberta. One of the biggest resources he has been getting are first, a lot of funding for him to build quite a good geochemical analytical facility there, especially in working on deep diamonds. And second, we're treating very small samples. And the second is that he got a lot of access to the Canadian diamonds, especially in the northern part of Canada. But I also have other international collaboration to gather super deep diamonds, mainly from Brazil. So about this work in particular, that they have not directly worked on diamonds, but they work on something that is relevant to diamond formation. So let's look at what's the idea of this paper and what I think is new from this contribution. And for this work, they combine two topics together. One is about the fate of the continental lithosphere, so we shall call it craton. So craton refers to lithosphere that is very old and with very low density. Old, I mean, mainly from the evidence of those crust. So all the cratons around the world, they do have the Archean crust formation, very old, more than 2.5 billion years old. And they have thick lithosphere, so with lithosphere thickness of 200 kilometers or even deeper. And they also have a low density and therefore low geotherm, because if we assume the asthenosphere below it all have the mantle adiabat temperature, for example, 1300 degrees C or 1400 degrees C. And for this part of the lithosphere, their temperature relatively lower. So for these cratons, they are crucial for why we have continents, because if their density is not low, then everybody, including us, will be sitting below the sea surface, and we'll be sitting in water. Basically, we want to have the human civilization as what we have today. So for those lithosphere, a lot of research has been going on in the last 20, 30 years from the formation of lithosphere. So for example, this is just an example. The speaker also spoke at our same webinar last year. So they are to talk about that how the lithosphere were created or formed. So there are two ways for lithosphere to form. One is from the early Earth plume process, how the cratons are created. Another way is early Earth subduction process that created the early continental lithosphere. So this is how the cratons are formed. And when people talk, but when we look at the cratons around the world, for the eastern part of North China Craton, as well as the western part of Wyoming Craton in the United States, the cratons that do have very old crust, but have a thick lithosphere. So then people talk about that how those lithosphere below these two portion of the cratons that loose or let's say are not cratons anymore. So before this publication, people mainly talk about the process that, like say, subduction brings water, for example, into lithosphere, and therefore cause a lot of partial melting, and therefore change the composition of the lithosphere, and therefore the continental lithosphere no longer becomes thick. So the density becomes higher, and the continental lithospheric mantle becomes more like oceanic, becomes like the mantle beneath the mid-ocean ridge facade. And there are also ideas that the plumes could erode this continental lithosphere, and therefore these plumes, they are the cause for the cratons, like the eastern part of North China Craton and the southern part and the western part of Wyoming craton in the United States, of how they erode a part of their continental lithosphere. So for this work, they bring something new, that is, they want to say that the plume not only could reduce or erode the continental lithosphere, but the plume could also create the craton lithosphere. That the plumes could help the cratons that used to have low thickness, that no longer become such a thick continental lithosphere anymore, but could make it thickened to the thickness of 200 or 250 kilometers. So this is a quite novel idea. So basically, it's thinking of things in opposite way. So rather than plume being a cause to distract the craton, but plume could also be a cause for some part of the lithosphere to recraton, which is the title of this paper about the plume-driven recratonization that make the continental lithosphere to become thick again. So this is quite a novel idea and a novel mechanism. But the observation comes from it is interesting. So what they have been seeing here in this, why they get the idea is that if you look at the map, so this is in Canada, actually in the northern part of it, this becomes the Arctic. Actually, they are already in the, let's say, Arctic Circle, I think. So it's pretty north. And they do choose several spots, 1, 2, 3, 4, 5, as they have been reported samples from these 5 locations. So in this region, what they see in this black part are the Coppermine River basalts. So for this are large igneous provinces. So for this basalt, for them to be generated, this basalt normally should correspond to relatively thin lithosphere, because the basalts are generally being thought to be generated with a decompression, that is, with the upwelling of the sample. So when the pressure decreases, it reaches the solidus or the melting temperature of the mantle peridotite, and therefore the basalts are being generated. So this larger basalt, actually quite large if you look at the scale, that is a almost 400 kilometers by 200 kilometer scale of what has been preserved today. But this one, I think their ages is about like 1.2 billion years or something like that. And this large scale, that means that this part of the continental lithosphere, at least during the time of the basalt eruption, for example, 1.2 billion years old, should be with a thickness, for example, 80 kilometers or even 60 kilometers, similar to the oceanic mantle lithosphere thickness today. So that's how those basalts, large amounts of continental basalts, could be generated. Similarly, places like Bushveld, not really basalt though, but with a large amount of this erupted mafic magmas, and so that's like the Takan plateau in India too, and also large igneous provinces in southwest part of China, etc. Columbia basalt, which is further south in this map at the Washington state, actually in the east part of Seattle. So for those parts, that they have to correspond to a thin lithosphere, at least at the time of eruption. And what they have observed here is that if you look at a seismic observation work, they see, oh, for this part, they are continent and their lithosphere thickness is all thick. So they're all 200 kilometers or deeper. So that means at least now the continental lithosphere thickness is pretty thick. And by now, if the state was what it was today, and it's impossible to generate this large amount of slab basalt. So this is a controversy. So even without doing this work, we could expect that this basalt at 1.2 billion years old that correspond to a thin lithosphere thickness and later on it becomes thickened. So this work, they provide a intriguing and relatively new, is a new perspective, saying that this re-thickened process was generated by the plume. The plume helps for the lithosphere to regain its thickness. Furthermore, from the samples that are collected in this region with much older ages, I think, they also see that the craton was thick. So basically, the craton are expected to have the evolution of thick lithosphere, thin lithosphere to generate basalt, to return to thick lithosphere again. So they do have this two-stage of evolution process. So this paper, they try to provide some news perspective on it. And so the evidence actually they show are mainly three things from what I see. One is the rhenium and osmium work, and second is trace element work for the bulk rock. And third, what they do is doing the geodynamic model to showing that this is possible. So first, for the rhenium osmium work, so basically what they have been working on, or this plot shows us, with the horizontal axis of the residual depleted age. That is the age when the melt are generated from the mantle or are being separated from the mantle. So the vertical is the number of samples they have. Actually, they don't have too many of samples as what they have been showing here. But what we can see is that they basically do a very simple statistics to say, okay, some of the melt were extracted much earlier in the R10. So this is the much earlier ones, and then in the later ones, I say about 1.8 to 2.0 billion years old, there's another event, and then at 1.2 billion years old, there's another event. So basically, this is what that corresponds to the basalt, flat basalt, as what I see. So basically, there are several processes that occurred, at least in the region. So this is basically the data could be presented this way, but there are different ways to explain them. And another important evidence, I think, from my own perspective, is the most important evidence that have been provided in this paper, is that they want to use the trace element, such as iridium, YB, as well as ruthenium trace element data for the bulk rock. Here they also show the bulk rock in terms of aluminum oxide concentration. So the higher aluminum it is, that means the more fertile the samples are. So you're going to have more aluminum-related phases, for example, CPX or like say spinel, for example. And then when you experience more partial melting, if we assume the primitive mantle, the mantle haven't experienced anything, so it looks like this, then we expected that with the melt being extracted, the residual becomes have different ways of evolution. And it depends on, it's a pressure dependent process. So what are the direction that it has been shown to correspond to different degrees of partial melting. So, and what they are claiming is for the trace elements, they mainly look at rather than YB is the Lu, ruthenium. So when they're looking at that, the region is simple. They say, okay, so for these two elements, they are not easily modified by later metasomatic process, and therefore these two elements that preserved what it was, and so they follow the melt extraction process such as this. But let's come back to this one, because this is a major argument they want to make. What they want to say is that, okay, for this one in the center part of their plot, which they have shown before. So for this one, they correspond to very high pressure partial melting. And then with this concentration they preserve, they are not being perturbed by the later metasomatism process. process, and then therefore they could trace the thickness, trace the depth of the samples when they are being, let's say, formed. So although these samples, they are no longer coming from so deep, but they think that they come from so deep from their trace element concentrations, because they could be, or this is a reasonable explanation to explain that they are being formed at 7 GPa with certain degrees of partial melting. So this is another important evidence where they have been preserved. So this is number 2 evidence they have. So number 1 is osmium resonance dating. So that's one evidence to provide. The second evidence is the trace elements concentrations of Baku rock. Like I said, they plot in different way. And meanwhile, they also use major trace elements published before and put in their thermal barometer and then calculate their depth. So basically what they are looking at, actually, I'm not so sure for this part, maybe I haven't read it as clearly as well, is that they want to show this, actually, only few samples that lie at a high pressure member that they are. Most of it is from the relatively shallow part. My interpretation for this is that they want to say is that these samples that are coming from all over the samples and all over the different depths of lithosphere. And then when you calculate temperature, you could create a geotherm that how the temperature increases from 0 on the surface, I mean almost to 0 degrees, to much higher temperature in the interior until you reach the adiabat. So I think this is still, like say, reasonable continental lithosphere gradient, so how the temperature, the reasonable increase. So these are 2 major evidence that they have been provided. So here is their explanation. Even before I go to the geodynamic work, I want to say, let's say they then jump first. They jump to explanation for this before they do the geodynamic work. That's my interpretation. So what they want to say is that, okay, if the samples are coming from, should be generated at so deep at a 7 GPa, and my interpretation is that if those samples, a lot of them are not from so deep now, then that means this trace elements means that those samples are coming from somewhere here, and then they are being upwelled to somewhere here. So upwelled, for example, 100 kilometers or more. And so they come out with the idea, so why not? Was the plume that comes in that it could generate a basalt, but meanwhile, let's say they think that they erode the lithosphere, but meanwhile, they also created partial melt somewhere here. And therefore, for those deep samples, like say created like say 210 kilometers or 240 kilometers. So those samples that are being brought up by about 100 kilometers. So that's why we see the lithosphere with both the basalt, and later on we also see this lithosphere thickness as those low density continental lithosphere are still the same as what they used to be. So they first threw this idea, then they jumped into geodynamic modeling. And for this one, actually, I'm not geodynamics, I could not judge in the detail. But if you read the comments for this, they reviews for this paper, actually it's interesting. I think it's a good thing. They present the peer review as well as their corresponds to the authors in the online that you can directly read them. So from the several reviewers aspects, that's what I see. Maybe I'm going to just directly read them. Review. So if I'm going to yes. So for example, one of the reviewer who is a geodynamic scholar will say that if you do have a clear conceptual idea, and then you can always, then it's easier to get a geodynamic model that could satisfy your conceptual idea. But however, there are many free parameters that you play with, and basically you are not sure that which ones that really correspond to that of the Earth situation. So basically, if I just take from the reviews that this part is more like a proof, like a weak proof to what they have been showing on. But I think it's fine. So the conceptual idea they put for this one is that the continental lithosphere could regain its depth after the plume that generate a very deep melting somewhere here and leave the residue here and let it up well. And then using that, you will coming back to say, that's the reason why we see the surface geology looks like this. And the seismic observation looks like this. So furthermore, they collect the samples from different locations. I think one good thing, I think it's close to the truth, but it's always an argument that geologists would like to put it here is the mantle heterogeneity. So in this region, the region that the plume generated is not uniform. So for some regions, the plume has a larger effect, and some regions, the plume has less effect. So what they think is that in this region, for example, that's likely, in my interpretation, the center part of the plume, where for the other parts that are not necessarily the same, and the plume that hits different part differently, and to me that's the only part that generated basalt. So that's part probably become thinner the most, and then so this, to me, that this paper also wants to argue that if this part does become thin, that this part that actually, to me, I don't understand this, because for this part, for the Parry Peninsula, if it has not been affected much by the plume, that it didn't generate basalt, then it should have a thick lithosphere. And then for this part, if the lithosphere is recratonized, then do they want to claim that this is the mechanism that makes this lithosphere thicker than this one? So the Artemisia is thicker than the Parry Peninsula. So let's see. Actually, it did hit it. So, okay, then I don't understand this now, because time doesn't match. Because I'm wondering that if you want this mechanism to explain this too, then how you explain this one, Delvic, which is thicker? Because for this idea is that they want to have the plume to hit part of the craton and then recratonize it to make the lithosphere thicker. So if you think that this part that becomes thicker, that this one is thinner, then the plume only hits this part. So they don't consider. Interesting. I don't fully understand this now, for how they are going to explain the details for this. I know that they are trying to claim this mantle heterogeneity, but now I'm a little bit confused by the walkway. What's the walkway plays a role here? So why the walkway does not create? So what makes the walkway is I say mountain building process, I suppose, that could create some information in the mantle. I don't know who could answer my question.
Now, these osmium model edges, these are also different. I mean, for Diablo Craton, it's significantly straight, whereas in case of Peri or uh, I don't say Artemisia, in Artemisia, these why there is a gap there in Artemisia?
Sorry, Chuking, I cannot hear you very clearly. Could you type? Could you type in the chat? Or if any other ideas or questions, you are free to type or open your mic. Because this is a paper discussion. I mean, it's not that formal, but it's good that we could talk about it so that when the speakers speak, we'll have a better understanding of the paper. Because we will go into the seminar with some questions in your mind. So that helps with the experience of the talk. So in this gap between the two, I don't know, because I don't know what's the geological activity people are sure to have. Because what I see is that they are all more or less sure that they have the Macan Sea plume or event. But I don't know, do they have this two event? I mean, Archean, I don't think there's any event at all. So this is not the event. I don't know. Because this model ages that could be created by different factors. So if nothing happened, then you should not see any distribution. Then suppose there was old activity somewhere here, it looks like this, and then have a new activity, perfectly we could see the bi-model distribution. But the real case is that it's just going to mess up with a lot of the previous process, and you might see a lot of difference spread out. So having this, to me, doesn't necessarily mean, if you only look at this one, doesn't necessarily mean there are three events. It has an indication, maybe say it has three, maybe it's just two, a combination of the two. And then have this some other peak. But if you look like this one, that if we think this 5 places all experience the same thing, then this does record another event. But I don't know what this event is for. Whoop, I don't know what you have been reading. Let me see. If now you're going to help me to understand it, then I have to look for help for a paper myself. Okay, so it is a subduction event. I think, let me see, reference 26. Let me check. So there is an event here. Basically, they do have another event that they think this one is subduction related. So, but the subduction haven't affected this one. Maybe it has been affected, but later on the plume that you rolled all the signals away. So that's my direct interpretation to his question. But let's see what they explain. So they do have some part to explain. Yeah, okay. So the paper explanation is that, okay, it has been eroded away. It could have, but it has been eroded away. Yeah, what they say is that a 1.8 billion year event, Orogeny event, weakened the lithosphere, helps the lithosphere unless part of it to be eroded. But for the signature of osmium or model age, that later on, then I can see plume activity. Basically, erode the Artemisia. But yeah. So you should add, okay, because in this part is affected the most, I think. Because for Artemisia, when they showing samples here, I say it has a closer location to this one. Okay, but it doesn't necessarily have the thickest lithosphere. I hope that they would say that it has a very thick lithosphere, but it's not. The central part is here. So the plume only see this part as a big lithosphere thick, become thinner, and then only affect this part and become thicker. So that's, I think that's what they say too, right? They want to say that this is a Creighton block, this is another Creighton block, this is not another Creighton block. Maybe I'm missing some information here. This is one, maybe this is another one. 100 kilometers. We have some the middle zone in between. Yeah, myself, I don't fully understand this when they try to explain the regional heterogeneity with their data. Okay, will keep my mind active. If you could contribute some points, that would be great. If not, then I could only look for the speaker when he speaks to see the difference. So which one? You mean all? Actually, now I do have a question of which ones are broke. I think this one other than this one, the Central Victoria Island, did they say this one has been destructed? They want only say this one being destructed. Actually, now I get more confused now than, let's say, what I thought I know before. Because I'm not clear now which part are they claim to be destructed and then regrow. It doesn't look like all these points experience that. I don't think this one, for example, this Central Victoria Island, I don't think it has been destructed at all. To me, maybe influence a little bit, but not that much. And this one has been affected by the orogeny. So they would have subduction. They put some crustal components, maybe some, not necessarily crust samples, but maybe some volatiles here. And then helps those lithosphere mantle to be eroded away. So that's my interpretation for it. So sorry, Ben, could you repeat your question again? Thick. The diamonds have to be on the thick because the diamonds, so normally comes from somewhere here. So the lithosphere have to be thick to have a diamond stability zone. So basically, I mean, so normally people want to say this. So you normally want to say, okay, this is reaching diamond stability zone. So when you have the diamonds, when they put a strong argument for when you have the diamonds, that means the lithosphere at that time of the sample that your lithosphere, the lithosphere is thick. So I think they do have that part for the Phanerozoic samples, but I'm not sure that they do have the samples. Do they have the xenoliths at the 1.2 billion years old or 1.8 billion years old? Okay, but to my understanding, that the xenoliths are all young here. Yeah, you see this one. I think I'm still sharing my screen. So they say that the thickness is held close to the original thickness by 616 billion years ago. So to me, that means the xenoliths they collect were the xenoliths containing diamonds. They come from the samples that are 616 million years ago, or million years, or younger than that. So that they say, okay, by this time, this becomes thickened again. But they didn't say that what it was before. I mean, it is totally possible that there were no xenoliths at the time. Okay, they do have some more information here. Modeling. Now Now this region, my understanding that now the lithosphere in this region, they all looks like the continental lithosphere. So they don't look like the mantle contains crust. They looks like a continental lithosphere mantle. They don't look like an oceanic lithosphere mantle anymore. Since actually not now, I think since 600 million years ago until now, they have low density and very depleted compositions and thick. Like the oceanic mantle, you mean? The thin lithosphere, yeah. That's why it generates basalts. Because if it is as thick as today, 200 kilometers, it cannot generate basalt. But to me, it looks like, okay, if we combine with the comments that Tu Hing put it here, okay, so Tu Hing put it here saying that it hits some regions not. I think they also explain this figure they want to show here. So they want to say, okay, for 2 GPa, for some samples that here following on this array, maybe North Atlantic craton, for example, actually we put global cratons here, actually including some of the cratons here, Dalvik here. Let's say these samples that are created by the 2 GPa, 60 kilometers, or 3 GPa, 90 kilometer polybaric melting. So these samples, they are coming from shallow, and these samples, they are formed from shallow. That doesn't mean they come from shallow. They form shallow, and these samples, they form from deep, 7 kilometers. So do this paper only mean that only in this region, Artemisia, only in one region, that the recrystallization process occurred? It doesn't mean the entire region. Also, the title claim, the recrystallization only occurred in one region. And they want to explain that only in this region, Wakpe origin, in this very small window between these different blocks, the lithosphere was thick, was thick at Archean, and with the thickness maybe 200, 300 kilometers, and then turned to thin parts, maybe 80 kilometers at 1.2 billion years, and then at 600 million years, it becomes thick again at the depth, like say 200 kilometers of what it is today. And for the other regions, the plume only weakened, like say, eroded a part of the lithosphere, but not too much because they are not at the plume head. So if that is the case, then my interpretation is that this geodynamic modeling showing here, so for this plume head, so the distance between this one, this region to this region, so the distance of these two, maybe it's only 200, 300 kilometers, as what they are trying to say here. I mean, so the geodynamic modeling that they are doing only limits its application to here. So Artemisia is just like at the edge of that geodynamic modeling. If you go further at the Jericho, then it doesn't apply anymore. That means this already outside the plume head. And only in this very small region, this very small green region, this Artemisia is like the edge of the green region. And only in this region, the plume hit, erode the part of lithosphere, and then the lithosphere being regrown again. Okay, my interpretation is that the paper says something like this. And for this one now, as well as all the other parts, they're all continental lithospheric mantle. Now, okay, they don't have much. They don't have much crust components. So one thing, yeah, okay, go ahead, please, Ben. I think we ask the speaker, ask his opinion about it. My interpretation is that of course, the crust, the basalt composition, the flood basalt composition is affected by the crust. It's contaminated. But normally people try to get rid of that and then try to look at it as a source, primitive composition, and then calculate the depth. But my idea is that they could not come from too deep. For example, if it is like, let's say, 120 kilometers, you cannot generate the basalt from so deep. So you have to generate at much shallow part by decompression to begin with. So whether that basalt, how much of it has been contaminated is another thing. I think it's a two order of control. So I think for this paper, they point out to a very good thing. So I think for a lot of good geology questions, they're just like that. They begin with some very simple and generally agreed observation, and then come out with a conceptual model. Then they try to find a good explanation for the model. So I think this paper that follows that track pretty well. At least this part of observation, surface geology, as we can see here, is relatively solid. And so I think it's pretty interesting study. So yeah, recrystallization at selected areas. To this paper, they say the recrystallization at the selected areas with the plume head or where the plume hit the most. But the one thing that they exclude in this paper is that metasomatism doesn't affect it too much, because otherwise they could not explain this, right? The whole rock composition, YB and LU, ruthenium, iridium contents. So they could not explain that. So if Ben could come out with the idea of other metasomatism could change these two element compositions, then you are going to mess up their evidence, because this is the core evidence they have to say it comes from 7 GPa, from very deep. So that could support their recrystallization model. So if you could come out with the other metasomatism media, I don't know whether carbonate could work, carbonate melt could work, or some other. I don't think the water fluids could work though. But Ben maybe could think about it. If you could think about where the YB and LU could locate, you could find other explanation of metasomatism. And then basically this paper, this model could be, the data could be interpreted in another way other than the, let's say, pressure induced melting. Okay. Okay. So Lei asked a question, whether universal phenomenon. Yeah, this paper, I think the reviewer is also, the reviewer also asked her about this. I think I highly recommend you to read the reviewer's comments. I think that they're all going to say how general it is. Explain the general application and fully explain the original. let me see, universal. I think somewhere to it is the general. General the process it is. So this is a reviewer's point. Actually, I think it's pretty interesting when I read about it. So yeah, I think it's a very good question for how general it is, because it looks like only between very old blocks, this recrystallization process could occur, as what they are explained. Let me see, generality. So to me, that the generability of this paper is about the stability of the cratons. So rather than the cratons being recrystallized, so they want to basically explore put new insights for how the cratons are stabilized, and does the age of diamond formation have anything in relation to this? I think that's another good question, because if we expect, actually, I think this brings some other things for people to think about too. I don't think this region have super deep diamonds, but if they are right, then we should expect to see that the diamonds with like 1.2 billion years old. I do think that they could generate diamonds in this region, but I didn't look at the detail. You could ask the speaker, right? What's the age distribution of diamonds in this region? And if the speaker is right, as what they claim for, so then they are bringing stuff that are coming from really low, deep depth. I mean, somewhere here, maybe 300 kilometers, and bring it to 200 kilometers. Then if diamonds are from there, then we are going to see some inclusion from really deep, fairly deep, to, let's say, the depths that are shallower. So if this is true, then in this region, in the published region, Artemisia, then we should be able to see diamonds with this age, 1.2 billion years old, or younger, or even younger, or the new ones, maybe 500 billion years old, coming from really deep. So young diamonds should come from really deep to support their hypothesis. I don't know whether this is mentioned in the paper, but we could hear what the speaker is talking about. I think, Lei, I highly encourage you to ask this question. Think about it. This is related to diamonds. I think diamonds are a very good way to test their hypothesis, to test their model, if they are right. Okay, so at least from what I see, is that if it is self-consistent model, then, sorry to click too much. And if the self-consistent model, the Artemisia diamonds should be deeper than all the other 4 places, because those diamonds generated by this plume recrystallization process, part of it is coming from really deep, 300 kilometers brought it to 100, 130. So that's my interpretation, but you could think about it. Okay, I think it's okay. We have been talking for a while, but that's okay. Okay, that's all about it today. And yeah, thanks everybody for the participation, for your contribution, for the ideas. And next week, Lei is going to lead a discussion on the nitrogen in the Earth's mantle. Okay, that's all for today. Have a good week.